So it's my great honor to introduce Professor Sawyer Fuller from the University of Washington, Seattle. And he creates biologically inspired sensors, control systems, and mechanical designs targeted at insect-sized air and ground vehicles, and investigates flight systems of aerial insects. He completed his PhD in biological engineering at Caltech, and his bachelor's and master's degrees at MIT, and his postdoctoral training at Harvard. So he overlapped with me a little bit in that regard. His work at the intersection of robotics and biology has appeared in Science Magazine, Proceedings of the National Academy, etc. And I would say I just read a biography of Benjamin Franklin. This sounds like something Benjamin Franklin would do.
Oh, Chris, did you want to add anything to that intro?
Sawyer's super awesome.
Excellent. Perfect send off for Sawyer. Thank you, Chris.
Okay. Thanks, Eli. My name is Sawyer Fuller, and I direct the Autonomous Insect Robotics Lab at the University of Washington. We are very focused on creating viable insect-sized robots like this one you see pictured here. And because a picture never really does it justice, I've got a physical copy here. You can probably see in my video. There's nothing quite like seeing somebody hold it. So this is the size scale we're talking about. This robot is 150 milligrams roughly. It's got a couple sensors on board. And for a sense of the mass of that, that's a little more than a toothpick. So that's what I mean when I talk about insect-sized robots. Why would you want to do that? Let's start with that question. Why create insect-sized robots? And the part of the answer is that there are applications which, for robotic applications, for which if you could reduce down to the size of an insect, you might have some improved capabilities, particularly in the area of environmental sensing. They're smaller and cheaper potentially to build because they have lower materials cost, potentially safe around humans because of the lack of impact hazard. But one of the things that really interests and excites me about them, what sets them apart is the potential, which I'll talk about later in the talk, to work by harvesting energy from the environment. And the reason that might be possible is because they require so little power that ambient energy sources like solar power and maybe even Wi-Fi, well, they're too weak to power larger drones, but they provide a tiny amount of power, which is the sort of power you might need from insects to power an insect-sized robots. So they're in this Goldilocks regime, I would say, small enough to do this energy harvesting, yet still large enough to carry a full sensor suite thanks to recent and extreme miniaturization pressure from the consumer electronics industry, making them quite interesting from a robotics perspective as well, because we can start to think about making them autonomous. And we anticipate from this, think about a future of insect robots where they are ubiquitous and operating on a persistent basis, doing things like searching for disease outbreaks in crops, monitoring indoor and urban air pollution, or searching for fires, just to name a few examples. But I wanted to, before I go on, highlight two real central examples of applications that motivate the work in my laboratory. The first is illustrated by this oil and gas refinery. Just imagine your job is to keep this refinery from leaking. You have to find all leaks in a place like this. They could be anywhere, up high, back in corners, and so on, multi-stories up. We think this is a great task for insect robots because, first of all, it can be performed using simple biology-inspired behaviors that do not require precise localization. Because the robot just needs to be able to sense the gas and move toward its source. And it's also aided by this potential ability to operate persistently because these leaks could spring up at any time. So in the envisaged scenario of this application, perhaps there's a leak that it manifests as a plume passing through the air. And you as a leak finder would arrive at the leak detection site with a pelican case full of these insect-sized robots. You'd open it up and they would scatter randomly, flying around until one of them detected a scent. Then when it found it, it would do a so-called plume localization search strategy, maybe casting across wind and flying upwind when it detects smell, and then fly up the wind until it found the source through some mechanism, at which point it would land potentially and emit a radio frequency beacon that then a human operator could then find and then presumably patch. And this potentially could reduce greenhouse gas emissions, for example, and hazardous gas leaks. So this would be very nice to have this capability. The other example I like to think about is what about ultralight, massively parallel robots for space exploration? And this isn't my idea. This was first proposed by Anita, Flynn, and Brooks. Anita is I think was at Berkeley at the time. They wrote a paper in the 80s called Fast, Cheap, and Out of Control, a robot invasion of the solar system. They envisioned exploring the solar system using ultra tiny lightweight robots, something like what we're working on. And the real benefit potentially, and there's some technology we need to develop to deal with the extreme temperatures in space and so on, but the benefit here is ultralight robots. Mission costs, a huge source of mission costs to planetary exploration is in the price to get something out of Earth's gravity well, something like $10,000 per kilogram. Well, if you have a robot that weighs less than a gram, you've got a pretty low launch costs there. So there's some potential for, that'd be great if we could think about democratizing space exploration by drastically reducing the cost. Lastly, both of these applications and the application I'm most interested in, or the kind of area I'm most interested in, we're most interested in is flying. And that's because when you're flying, then almost any obstacle can be surmounted. And because it's possible to come very close to sensing targets, which potentially allows you to reduce the sensitivity of your sensor to make it smaller. Okay, so those are some applications. But there's more to it and more to why I'm particularly interested in this. It's also interesting because it's hard. So why is it hard and why does that make it interesting? And the bottom line is because small is different when it comes to robotics. Here are a couple, just to paint a broad picture here, a couple of examples of where these so-called scaling effects come into play and affect the fundamental physics of how the robot works. So for example, I could talk about, if I think about a robot of size scale L, like its wingspan L, then to first order, its mass varies as the length to the third. And so that's an example of a scaling law. Roughly speaking, if you take the size of a robot, you can draw a line that connects the different robot sizes according to, roughly speaking, they scale with mass. Their size scales with mass. So in the area of mechanics, we can talk about surface-dependent forces like friction start to become larger as you go to small scale. And so then if you think about the relative effect of friction compared to the size of the robot, the mass and the inertia of the robot, it becomes larger and larger as scale reduces. This is this L to the -1 here term. So friction becomes larger and larger at small scales. What that means is at small scales, we have an unfavorable glide ratio. So what you see in small animals is that they by and large hover. Hummingbirds and bees and flies are an example of this. It's also unfavorable to devices, mechanisms that have pin joints that require sliding, like a spinning propeller in an electric motor. So, so that's kind of the side of mechanics. We can talk about control and sensing. Similarly, we have a very limited power budget for our sensing and control because as you go to small scale, you can carry a very small battery, and so therefore we're talking about very constrained sensing and control power available. So like I mentioned, the upshot is that scaling means the scaling effects that start to really manifest themselves at insect scale mean that many technologies that have been put to great success on larger robots aren't really available at all in insect robots. So this is a challenge, but also an opportunity to invent entirely new ways of doing things, which to my mind is quite exciting. The good news amongst all this challenge is that we're in the very fortunate situation that in this particular case, it can be assured that what we're after, an autonomous insect-sized robot, is indeed possible, because most of us are aware that almost every day we see some sort of insect moving around. So we know it's possible. So that's the good news. So I direct a lab at the University of Washington that is focused almost entirely on this question of how to create autonomous insect-sized robots. In particular, we have, and I think, of four main questions that we are tackling, and about which I will give examples of some of our contributions in this area. Starting with actuation, how do we actuate these things? And talk about moving on to what sensors might they carry on board so that they can control their motions. How do we control it? What sort of control architecture? And then maybe a biggie is, how do we power something this small? Okay, let's see. I think I had a note here. So just a remark to date, this is all motivated by the fact that there has been no real examples of robots below a gram that have any significant degree of autonomy, or in terms of either sensing and control or power. So this remains an open area of research. Okay, so here are some questions. I'll talk about some of our contributions in these various ones. So let's start with actuation. That's probably the place to start here. So actuation. A brief history of flying insect robot platforms, and brief also includes the term incomplete, as all histories have to be. The work I'm describing here traces its roots to a Muri grant to create a micro-robotic fly given to Ron Fearing in Berkeley, maybe 20 years ago now. And along with him were my PhD advisor, Michael Dickinson, a biologist who's since moved to Caltech, and Shankar Sastry, who was the advisor of my other PhD advisor, Richard Murray. What Fearing recognized in the process of aiming to build this autonomous flying robot, and I think it was very much correct in this, is that there are two important things. The first is that semiconductor-based lithographic fabrication is maybe a little bit too much and too small for insect size. And instead what he focused on was a slightly larger scale where he could use short wavelength like laser micromachining. This allowed a very fast machining time of just a few seconds per part and an almost unlimited material set. And the other thing he recognized is that down at the scale of a fly, he needed to rethink the actuator technology, leading him to use piezo actuators, which become more efficient as scale reduces relative to electromagnetic motors. His first prototypes were pretty clunky and made of metal, but after a few years, they had dramatically refined their process, and they were starting to make composite-based little flapping devices. Let's see, out of carbon fiber composites. One of his grad students, Rob Wood, went on to found a lab at Berkeley where he refined the process a bit more and realized a nice innovation of making the angle of attack of the wings passive, and this allowed a much simpler mechanism and allowed the robot to generate the first lift greater than weight at this tiny scale. And this robot, I think, was 60 milligrams. A few years later, and lots more refinements later, and after I had joined as a postdoc in his group, we achieved controlled flight, as shown in this video here, which we had the great honor of having appear in Science. And then a short while later, I started my own lab, and where kind of one of our big contributions, which I'll talk about more, is the first wireless flight. You'll notice there's a little wire hanging down from here. So here we had to integrate a tiny power system on board. And this is a laser photovoltaic that we use to send power to this device. Briefly, a bit about fabrication before I go into design and actuation. Our fabrication process also it comes from process, I think, let's say popularized by Ron Fearing. He called it smart composite microstructures, and it includes this laser micromachining of flat sheets, rigid flat sheets, and then bonding them together with sheet adhesive along with flexible sheets like this yellow capped on sheet here, and then putting them back in the laser and releasing parts. So you get this foldable origami-inspired articulated mechanisms that then maybe you fold under a microscope with tweezers. Here's how the piezo works in a nutshell. We use bimorph piezo actuators, and what you need to know about piezo material is that it's a material that if you apply an electric field to it, it shrinks by a little bit. And through a cantilever configuration, you can turn that little bit of shrinkage of I think a 1 in 1,000, and you can cause the tip to bend depending on which of these two bimorphs, halves of the cantilevers, you activate with an electric field. And then you add one more layer of geometric amplification with what do you call it? A transmission. This is a simplified version of it that amplifies that tiny tip motion into a large wing flapping motion. And then on top of that, so this is what those piezo actuators look like, example piezo actuators. And then this is what the wing looks like when it's actuated by this piezo. And so the stroke angle is driven by the piezo actuator, and the angle of attack is allowed to rotate passively and bends like this due to the effect of aerodynamic drag. And this gives you basically the wing kinematics you would look for. And this is essentially the same mechanism by which flying insects actuate their wing flapping motion. So soon after starting my new lab at UW, one of the downsides we discovered with the Harvard RoboBee design, which was admittedly, this guy was the first one to was precise enough to get controlled flight. So it was a great design, but it required a whole bunch of parts. In fact, it required 21 tiny little parts, each of which were easy to fling across the room if you held them wrong with tweezers. So this does not favor, it does not make it an easy device to build. What we realized is that actually it might be possible, and it was, to take a lot of those parts and unify them into one single laminate sheet. And so that forms the basis of the UW RoboFly, which is a redesign, a rethink of the RoboBee. And the way it works is all of the transmission and mechanisms parts to hold the piezo actuator are in a single laminate sheet. This is what the layup looks like. The sequence of folds, I should say, the sequence of folds that make this three-dimensional structure. Drop in a piezo actuator and then glue in a wing. And with this, we've got a dramatically reduced part count of only 8 for a whole fly. And we had 2 of these together to make the RoboFly at the expense of a few more layers. What this gives us is a route to mass manufacture, which we very much like to eventually be doing. Okay, let's see what else. Okay, so that's great. So we cut the parts down and made it much easier to make. We've also been exploring how to facilitate building these and expanding their capabilities. So one of the things we found, or we know from flapping wing robots, is that the mechanics of the wings are very complicated. And it turns out slight manufacturing irregularities make them quite variable from fly to fly. And so it turns out that unlike propeller-driven drones, calibration turns out to be essential every time you build a new one of these guys and fly it. So we said, well, maybe there's a way we can automate that. So on the left is a video of how we did that, and it starts with a video of what it looks like when you first turn on first turn on the robot without any trimming. And as you can see, it flies off into the corner. So we built this device that uses motion capture to trim it and an active feedback loop. So essentially what you see is an adaptive controller that's sensing and correcting for this torque that's observed by the motion capture arena. So when it first turns on, it's tilted. Let's see here. First turn on, you can see it's quite canted, and then it slowly learns how to level itself. So once it's learned and eliminated these bias torques, then now it flies basically vertically, which is very nice. And now we plug those in to our flight controller, and this is what it looks like under controlled flight using those trim values. So now we've got a way to rapidly and consistently trim robots by essentially gluing them into this little device, running a special piece of code, and then you just break the glue joint with a soldering iron, and then the robot flies on its own. Another thing we've been working on is exploring other modes of locomotion. And what we discovered is that with our new RoboFly design, which lowers the center of mass of the robot much closer to the ground, more like a fly, well, it turns out you can use the wings to make it walk, push itself forward. And the way that's useful is now you can start to think about multimodal. Here is a video of it walking under a floor, under a door, I should say. And as you may know, opening a door turns out to be a pretty challenging task for a robot. So we've made an end run around that by making a robot that's small enough that it can just walk under the door. So getting through doors, problem, check that one off. Okay, other advances. This is a video of the Robo B under controlled flight. And if you look closely, you probably didn't notice this before, but it's wiggling back and forth around a vertical axis. And that's because we actually didn't have control over the vertical degree of freedom in this robot when we built it. And we actually had to make great efforts at creating a nonlinear controller that was able to effectively work regardless of the orientation, with this provision that we didn't have control over the yaw degree of freedom. So in theory, and we wrote this in the paper, you should be able to control yaw by flapping the wings quickly in one direction and then slowly in the other direction like this. And air drag on the wings goes as the velocity squared because it's a inertially dominant flow, inertial flow, high Reynolds number. But in practice, it turns out that there's some other confounding effects that really limit that effect. So it's a very weak effect. And it actually can't overcome, in this design, the effect of wind and this wire tether. It's very flexible, but still there, wire tether. So to overcome that, we just said, well, let's reorient these actuators in a new design. This is the robot called the RoboFly Expanded. And the actuators are oriented horizontally rather than vertically. And what this gets you is that now you've separated the wings farther apart and you've increased the moment arm. And here we are demonstrating for the first time, many years after the science paper, the first insect-sized robot is able to control its orientation, yaw control. So here it is doing open loop control, just turning left and turning right. And then here it is, you'll see it turns on at random, they both turn on at random orientation, and they very quickly orient to be at a set point facing to the right. This is slowed down by 10x here. So I can tell you this may not be that exciting, but I was super excited to see this when Yogesh, the student who was doing this, got this to work. Super cool. Why do you want to be able to have heading control? Well, lots of reasons. Talk about why it makes control easier, but maybe you also want to steer a sensor in a certain direction or steer your landing gear and land in a certain way. So it really is valuable to have yaw controls, the ability to control yourself around a vertical axis. Okay. We have, moving on, we've also been exploring, oh, this should not be there yet. We've been exploring other modes of actuation. This is an electrodynamic thruster-based robot. And this was very much inspired by Chris Piester's group here at Berkeley. They created one using silicon-based fabrication lithography, we said, well, we've got new tech, this other laser-based fabrication. We can build things out of metal and carbon fiber. And so here we are, this guy, we were able to build this. It just barely takes off, but it does so in a part with a single moving part, and we were able to build this in less than 30 minutes. So that represents quite a speed increase in terms of manufacturing compared to the state of the art. So this is some just initial work on exploring other types of actuation besides wings. Next, let's talk about sensing. And let's check on time there. Okay. So sensing, we have the enviable position that I mentioned to you before, that we, thanks to miniaturization from the consumer electronics industry, some of these sensors are now small enough and light enough to, some of the sensors we might need are small enough and light enough to go on board a insect-sized robot. So to think about what the suite of sensors might look like, we can look to the fly, which is one of these virtuosos of flying animals. And you saw that fly, the sensory suite that the fly carries is by no means limiting. That fly is just embarrassing us in terms of capabilities. You saw that in that video, the fly was doing flips, but clearly under very precise control over its flight, and it even executed a perfect landing. So how does a fly do all this? So it's got a pretty sophisticated sensory suite, including these gyroscopic halteres. It's got these ocelli, which are thought to sense the sky. It's got antennae, which sense wind and also smell. And then it's got these large compound eyes, which one of the things they're known to use is, in the course of flight control, is this notion of optic flow, which is a measure of the speed of visual motion as the fly moves through the environment. This is an important cue because it can be potentially used to estimate distances to obstacles. This picture shows a kind of a cartoon of what the optic flow pattern might look like for a person walking down a sidewalk. Things that are close have a large optic flow. Things that are far away have a small optic flow. And then things on the side of you have more optic flow than things in the center of you. So you can use this potentially to steer and guide your flight in a very power efficient way.
Can you tell us about the gyroscopes?
What's that?
Can you tell us about the gyroscopes, the halteres?
Sure. It's a super interesting story about flies. So not all flying insects have these actually, but the ones that seem to fly the best do. The basic insect body plan actually has 4 wings, but flies, also known as dipterans, they're called that because they have only 2 wings. And they essentially, their rear pair of wings has become vestigial and turned to these little stumps that vibrate in phase with the flapping wings. And then it's got these sensitive force sensors down at the base of the halteres that are believed to sense Coriolis forces. There's kind of a debate there about exactly what they're doing, but essentially it looks like they can tell the fly its angular velocity in all 3 rotational axes, much like a 3-axis MEMS gyro does. Yeah, so then that opens up the question, what do bees do? Bees are an example of animals that do not have halteres, yet they manage to fly somewhere. So this is an open question right now. Tom Daniel, who's in biology here at UW, has suggested that the rear wings actually twist to detect angular velocities. Anyway, so gyroscopes. Did that answer your question?
I was expecting something spinning. I was expecting something vibrating.
They vibrate.
What's the mechanism?
They vibrate back and forth in a plane, and then it seems as though what I know of this is that you have, if you have rotations around one axis, the strain pattern as a function of time looks different depending on let's say the different rotation axis. So these guys vibrate back and forth in a plane, but they're different from a MEMS gyroscope, which vibrates a very small amount. these guys vibrate, they flip back and forth by almost 180 degrees. And that large flipping that they do is what allows only a single pair of proof masses to sense angular velocity in around all 3 degrees of freedom.
Very interesting. Thank you.
Sure. Thanks for the question. Okay, so here's our sensory suite, potentially a target. You'll notice that this fly, and this is good, this fly does not carry any depth cameras, does not carry any radar, does not carry any scanning laser rangefinders. And that's probably good because that means we can do what we need to do without those, which are great sensors for larger robots, but down at insect scale, they probably are going to be using too much power because all of them are emissive. So we probably have to restrict our attention to largely non-emissive sensors. As an aside, some work I did in grad school on the fly sensory apparatus revealed that when we blasted them with brief gusts of wind, they actually have a very active wind sense in their flight control system. And so we want to use that as well. We're probably going to use that as well in our flight control apparatus of our insect-sized robots. What the wind sense gives the fly is a very fast feedback measure of forward velocity that potentially improves the observability, which is an estimate of their flight status, which gives them the ability to have a higher bandwidth actuation and higher bandwidth sensing. And it turns out when we glued their antennas so they couldn't sense this wind, they showed they could still fly, which is unusual for sensory ablation, but their flight speed was much more variable. Yeah, so I guess this is the wind gust here. You'll see the fly flies in from the right and then slows down a little bit and rises up during this very brief 30 millisecond gust of wind. And then the fly recovers and flies off. Okay, so here's our conjectured sensor suite for hovering on an insect-sized robot. The good news is that a lot of these sensors are off the shelf, and if not, we've started to make them ourselves. Here's a 28 milligram gyroscope. They are getting quite good and quite tiny. Here is a laser rangefinder. Okay, so we have to maybe use for ease of control. We're going to plan to use one laser rangefinder to measure just the distance to the ground that allows us to avoid this ambiguity in scale that optic flow techniques have. They tell you the relative distance, but they can't tell you the absolute distance to obstacles. We'll add on, here's a tiny camera that we built, ultralight camera, 24 milligrams, in collaboration with Jeff Barrows over at Sentai. And here's a wind sensor that we also built that uses ultra tiny micro machine silicon strain gauges to detect deflections of this paddle-like appendage. So with all these, I think we can control our flight. And this camera is so light that we were even able to go off and put it on a live beetle. This appeared in Science Robotics last year. Here's a variant of that camera, and we actually used our same actuator mechanism for the RoboFly to steer the camera. And here's a little wireless board and all the battery on board too. Very tiny devices here. Okay, so now we've got the sensors on board, all of which are within the weight limit, the payload capacity of flights that we've done on our tiny RoboFly.
Are you going to tell us more about the battery? It looked like an interesting concept.
Let's see. Thanks for the question. I'll come back to the battery and the battery life prognostication for that. This is a off-the-shelf battery. I think it's about 500 milligrams. You can buy these lithium polymer. I'll talk more about batteries on insect robots in a sec if that suits you. Hopefully. Okay, so control. Here is a conjectured control architecture that I think is suited to insect-sized robot. Here you've got here's our various sensors here. And here's our optic flow estimator here coming into an estimator. And then we're estimating state. And then we're going to, here's a controller that produces signal commands that then drive the wing and body of the robot here. Briefly, a little bit about a conjectured controller. We can say, well, the dynamics are governed by these Euler-Lagrange equations, nonlinear equations, but relatively simple in that they don't have any discontinuities in them. Here is so this is just a diagram of that. Add in our sensor model here. Here are the 4 sensors. This is the gyroscope. Here's the laser rangefinder. This is the optic flow. The measured optic flow is a function of these state variables. And this is our airspeed sensor, which includes both the wind and which is perturbed by the wind, but also senses the velocity here. This is our set of sensors. So it turns out we can linearize these dynamics using this state vector here. And it turns out that this system is both observable and controllable. And this, by the way, I should say, this is a 2D system. And the reason we can consider this only now is because we finally have a controller that, an actuator. Now that we can keep a constant heading, we can now use this linear model, this linear planar version of the controller. If our robot was spinning around a vertical axis, this would make this linearization much more complicated. So this, by controlling the vertical degree of freedom, we can now use this nice linear controller, and that's nice because linear control is very easy to compute in a small robot. Okay, so moving on. So one of the most significant potential, so we're thinking about how do we do this all in a very low power environment. And here's a sketch of how we might be able to start reaching the computation limits of a insect-sized robot. And so one of the large sources of computation power needed is optic flow, like visual processing. It's a known thing. Processing all the pixels that come in from a camera is it takes a lot of computation, relatively speaking, compared to running a linear control law. So how do we get around this? So this, we proposed an interesting solution here. So essentially, to estimate optic flow, we're trying to estimate optic flow from raw pixel readings. And typically, the important class of estimators for this quantity, the optic flow, which is measured in radians per second of visual motion across the image of the camera, involves a nonlinear operation on the time derivative and the spatial derivative of these pixel readings, where L is the pixel readings. A classic mechanism that's well used is the so-called gradient method. You estimate optic flow by essentially dividing the time derivative by the spatial derivative to get this angular velocity estimate. This is the basis of the so-called Lucas-Conate method, for example, which is a generalization to 2D. But this has an important downside when you're thinking about super tiny robots, and that is that it requires performing a divide operation, which tends to be power hungry and also tends to be a very relatively slow serial computation on computers. On an ARM core computer, for example, it takes up to 12 instruction cycles to execute, whereas a multiply takes only 1. So an important alternative is to instead do this biology-inspired approach where you take these two derivatives and you just multiply them by each other. So as I mentioned, that has a great advantage that it's much less computation intensive. Takes a single clock cycle, for example, on almost all microprocessors these days. That said, it's not an ideal estimator, and it has some important downsides, chief among which is it depends on both the contrast and the spatial frequency of the texture of the image you're looking at. So it seems like that might be a game over for this approach. But Well, it turns out that if you look at real images, they tend to all have a very consistent power spectrum. I think it's f raised to the -2. So the frequency spectrum of real images, the power spectral density goes as f to the -2, or close to that for very many different images. And what that means is that even though you have this spatial and contrast dependence in your correlator on real images, this is, you can show mathematically that if you know the spectrum, you will always get the same answer. Your output of the correlators will depend on the optic flow and this unknown quantity that you would need to calibrate once. But once you have that number, you're fine. So this is appealing because now we've got this method of computing optic flow that takes much less computation than the gradient method. And so we've simulated this whole system with a Kalman filter and the LQR controller, and projecting a texture on the floor here underneath the robot, and then implemented both the gradient method and the correlator method on this simulated little robot fly, and it's able to make its way to a target position. And so
can you expand the
cool.
LQR acronym?
Oh, sure. Linear quadratic regulator. It's a type of controller that instead of canonical PID control where you're tuning gains, in an LQR controller you're tuning the cost function for how badly you want to weigh different costs, like your position error or your velocity error. Thanks for the question. So so here this guy uses much less computation. This guy down to only 500 kiloflops, and that's so little that we're down in the regime of a 100 microwatts, roughly speaking, on a general off-the-shelf microcontroller. And that's the sort of power we're thinking about. What if we're working on insect-sized, honeybee-sized robots like the RoboFly, which is about 100 milligrams. But down the road, we're curious about what if you go down to fruit fly, gnat size, 1 milligram robots. And now it turns out that this controller is maybe even lightweight enough to run a gnat-sized controller. And for a sense of scale, I've drawn a teacup in here. And so here's our gnat landing on the edge of a teacup. So the way we've done this 100 microwatt control is to do all visual and control computations exclusively in multiply and add operations. Okay, so trajectory generation, let's see, stabilization to hover. And so this should be possible to work in full 3D control. At the power envelope down at the sort of scale you might want to see in a gnat robot. So now we've got a hover mechanism there. And now once you've got a hovering controller and a set of sensors that allows you to hover and essentially fly stably, you can start building a lot more interesting capabilities on top of that. So this getting yourself in the air and hovering turns out to be quite difficult. But once you're there, you can build things on top of that. And here's an example of that. This is the Smellicopter, which is filling in the next phase. This helicopter uses a controller like that, and it additionally has the ability to smell using a moth's antenna, which in some ways is much better antenna smell sensor than any man-made smell sensor. And here it is using that antenna plus these wind vanes to steer itself into the wind. It's flying in a wind tunnel here, and this little dot is a source of odor. And so this robot is measuring tiny signals from the antenna of a moth to detect when it's in this plume. And when it's in the plume, it shows red here, and then it performs a surge up to the source, all while avoiding these obstacles here, which an obstacle avoidance is relatively easier to do than hovering. So once we've got our hovering controller, we can, this robot uses laser rangefinders to avoid obstacles, but you could imagine doing something very similar with optic flow. Okay, so that's the showing. Now we've got hover. I've got building on that. We can do plume source localization. The last part of the puzzle that I want to spend a couple slides on is power. And here we've got a couple of interesting advances here. So the first challenge comes from small scale actuators, by and large, require high voltages. Piezos are no exception. They require a couple hundred volts. So this robot, one of the challenges here on this first wireless takeoff was building this tiny high voltage power circuit on board this guy. And so that's what this guy has. Incidentally, this is also the first example of a sub-gram robot carrying a microcontroller on here. This is on here, which you can't see, is a tiny ARM M4 fingernail size processor on board as well to generate the signals for this boost converter. Let's see, version 2 just came out, and it's got 2 new capabilities. The first is that it has 2 drivers instead of 1, so now it can drive the wings independently. The other thing it has is the ability to learn through an adaptive means on how to generate sinusoid signals of different amplitude. And with that, we were able to demonstrate for the first time that you can actually modulate the thrust of our wings. And this is a foundational capability that we need to do something more than just open flight like this, but to be able to control flight by modulating the output of the 2 wings independently, so we can steer ourselves and fly in the air. So that's the power. That's high voltage power generation, which is a big challenge. And then lastly is how to collect and store power. This is an area we're just getting into, but again, as I mentioned, it's one of the areas that I think insect robots have the most promise. It's because they use so little power that they might be able to harvest these microwatt power sources that are available in the environment that are just too little for big robots. In terms of batteries, scaling doesn't really help us here. We don't expect a long flight time. This is a 140 milligram battery from out of the wood group. We'd expect maybe half a minute of flight time from that based on our measurements of power usage. Power Stream makes a 300 milligram battery, so if we scaled up our robot a little bit, we could probably carry this robot at this battery and get maybe a couple minutes of flight time. Not a long distance, but enough to do something like fly from one power source to another. And one important example of that power source is solar. So solar is a great example, another great example of where scaling helps you. So recall that the mass of your robot scales as L to the 3rd. And therefore the power needed roughly scales as, power you needed to fly scales roughly to first order with the mass you are. But solar power, which scales as the surface area, which goes as L squared, scales downward much more slowly. So as you go smaller and smaller, you get more and more power, relatively speaking, from solar panels. And at some point, you start being able to carry a pretty small solar panel and still be able to fly yourself indefinitely. So that's something we'd like to do eventually. In the meantime, we've been playing around with a larger drone that can power itself from the sun. So this is a palm-sized drone here. And we added to it some solar panels, and we built a custom maximum power point tracking circuit to charge the batteries on board. And so here it is. It was, we didn't have enough sun that day because Seattle, we have to wait sometimes to get sun. So we had to do this experiment inside. But basically what it shows is that it allows the panels can fold down to reduce air drag when it's flying, and then by using the ground effect, they flap out automatically when it's time to land, so it can collect sun. This robot has about a 10% duty cycle, but we expect that to be possible to do much better than that when we use better solar panels. These are very low efficiency amorphous cells. And then as we go to small scale, down to insect size, we expect to get better and better duty cycles. On the horizon, beyond solar, so solar is great. That's a very plentiful power supply. We can also, we're just thinking now about whether you could use sources like Wi-Fi, which are indoors. Wi-Fi access points emit almost always about the legal limit, which is 100 milliwatts. So if you can capture any significant fraction of that energy, then you have a significant power source that your insect robot can fly. Imagine it flies from access point to access point inside picking up power. Okay, so that's it for power. Okay, last slide before thanks. The conclusion here is that I've given you a number of kind of examples of some recent contributions in terms of sensing, power, and control of insect-sized robots. And we hope that these are going to lead to, in the next few years, robots that are actually fully autonomous and able to start rivaling the incredible capabilities of insects like flies. But more than that, I'm convinced that the future is bright, both from that perspective and also from the perspective that the innovations that we create in the process of solving these extremely space, power, and energy, size, weight, and power constrained systems, like the automation challenges associated with those, under these swap constraints of insect-sized robots, will produce dividends that extend across all of engineering. So thanks for your attention. With that, I'd like to thank the hardworking team at the Autonomous Insect Robotics Lab, my collaborators, and thank you for your attention to this. And I'm now here for questions.
Great, thank you so much. So we did get some questions during the talk. I'm going to go ahead and also if you have more, please keep them coming in. I'm going to ask at least the first one because it was from our very own Regina Baichi. I think she just had to log out, so I'm going to ask the question for her. But the question was really is sort of two different parts. One was just how do you really deal with the fragility and the lack of robustness of these systems? I think you touched on that a lot, but maybe you have some more thoughts on that. And the other kind of related question is, obviously you're dealing with really low payloads, very small. So how do you divide between sensing and actuation? I mean, how do you kind of decide the split for that?
Great questions. I will start on the sensing versus actuation. I'll start on that because that's a quick and easy one. Larger drones, by and large, you see this divide of about 10% devoted to computation and sensing and the rest to flight power. So that's what we're targeting here. I think I didn't mention this, but at RoboFly scale, the 143 milligram robot we have, when it's fully loaded, it carries, it takes about 250 milliwatts to fly. And so if we're talking a 25 milliwatt sensing and power budget for that size robot, which is feasible. And if you look at the gyroscope and the laser rangefinder and these other things, they all fit, their power usage is all under that 25 milliwatts. So I think we're pretty good there. Down to gnat scale, where we'll probably have to think very carefully or think about something else. The other question was fragility and lifetime. So what I will say is that we have hopes that they will actually be quite robust. And the reason I say that is because this is an example where scale really helps. You've probably heard the story of that an ant can carry 50 times its body weight, or whatever the number is exactly. And that all comes down to the fact that gravity and inertial forces are much lower as you go to small scale compared to rigidity, mechanical strength. That's why large animals have thick legs and small animals like insects have thin legs. It all boils down to that. So we believe that actually they're actually going to be quite robust because of the scaling. And we actually intend to take advantage of this by using control laws that aren't perfect all the time. If a large drone crashes into a tree, that's pretty bad news. You're probably going to lose that drone, or at least high chances, at least losing a propeller or something. You don't want to crash a large drone into a tree. Crash a fly or a bee or a RoboFly into a tree, you're probably going to be okay. You can drop that from thousands of feet up, and it's not going to be any more damage than if you drop it from the side of your table. The piezo actuators, they are brittle, so that's one area that we're actively thinking about how to reduce that brittleness. And there's lots of techniques we can use. That's something we want to improve on that. If you give them the wrong signal, they will crack. If you give them a high frequency signal, they'll excite their self-resonance and it will crack. Thanks for the question.
Great, no, perfect. I think actually that leads into, we had a question also from Dylan Acker James. Did you want to ask your question? I can kind of let you ask the question directly. Would that be okay? Because it relates to, you can go ahead probably.
Yeah, awesome. Great talk. I really appreciated it. I'm actually in Chris Piester's group, so when you showed the Ionocraft stuff, I was like, oh, like this is very applicable to what we're actually talking about now. But I'm curious for the RoboFly, you talked about it having 8. I wasn't sure if it was 8 parts for one wing or 8 parts for both wing and the body. And I was also curious, like how much skill and time does it take to make, like, could a determined 6th grader, put one of these together for like a class project?
They're still pretty, the RoboFly, right? They're still pretty hard to make. Most students in my group who are learning to make them fail on their 2nd or 3rd try, and about the 4th fly, they start getting to be good enough that they can do a controlled flight with them. So they're hard to make, and they get doubly hard if you had a cup of coffee recently, and maybe you're familiar with this, or if it's at the end of the day. So there's a saying. Originally, when I was in this business, I thought, oh, I'll do my thinking in the morning, controllers in the mornings, in the afternoon I'll build RoboFlies. You can't do that. You break them, you get frustrated. So they take a lot of concentration to build. That said, I think they're very amenable to mass manufacture using origami and pop-up inspired fabrication techniques, or like a pop-up book. You open it and it folds into shape. These kids' books, they have a single degree of freedom that actuates all this stuff. And so we think that something like that is going to be amenable to building RoboFly-like devices. Yeah, so the other part is the piezo actuators are quite tricky as well too, and they require curing the carbon fiber at a very precise rate. So you need some special tools there. And we'd love to figure out how to eliminate those tools, but we haven't figured that out yet. So we need a pretty sophisticated hot press to build the actuators. So not quite where a 6th grader could do it yet, but I'd love to get there.
Awesome. And then how many parts was the wing? Was it 8 for the wing or 8 for both wings and the body?
Let's see. It's 8 for, the 8 includes 2 wings, 2 airframes. So I don't know if I can do it. 2 wings, 2 airframes, 2 piezo actuators, and 2 extra legs to make it so it sits on a flat surface.
Gotcha. Okay, awesome. Thank you.
Great. If I could, I was going to go, Daniel Drew has a question as well. Is it okay if I'm going to let you ask directly? You should be able to do that now.
Sure. Hi, Sawyer. Great talk. Thanks a lot. I also make that joke about drinking coffee and assembling robots, so that's perfect. You mentioned that the—
Daniel, by the way, or at least hear your voice.
Oh, right, likewise.
Very cool.
Yeah, you mentioned that the low power flight controller would be suitable for a gnat or a fruit fly sized robot. I was just wondering if you had thought about kind of the limit of miniaturization of this piezo bimorph based flapping approach.
Good question. How small could you go with a piezo bimorph? I think you could go pretty small. It's kind of insane if you look at the size scale of how small nature goes. There are these wasps, I don't know if you've heard of them, the trips, that are rather smaller still than Drosophila. I don't know what the mass is, but Drosophila is maybe 3 milliliters. These thrips are like 1 or less than a millimeter, and they're so small that their brains, they don't even have enough room to have nuclei in the brain cells of their brain. So they once they get a certain level of development, they don't have a nucleus anymore in their brain cells, but they still can fly and mate and do all these things that insects do. I think that's probably the lower limit in terms of physical feasibility, in terms of the fluid mechanics. You start hitting drag, like viscous drag starts to become more and more important. So I think there's no reason we can't get down to that scale. Below that, I don't know if you want to use flapping wings anymore. You probably want to use something else, like just electrostatic forces or something, or just rely on the wind or something. That's my sense. That's what spiders do. They just spin out webs and they use, there's actually an electric field in the atmosphere, and they're thought to just use the field in the atmosphere to pick themselves up.
Great.
Eric,
Thanks,
can I
Daniel.
ask a question?
Yeah. Oh, yeah. Sure. Sorry. Yeah. I'm just trying to work
Okay.
through them, but go ahead. Yeah, of course.
Yeah. So the period of staying aloft depends upon the energy to mass ratio of the robot. For example, the quadcopters can stay aloft for about 20 minutes, and it's related to the energy to mass ratio of lithium batteries. So I'm wondering, why can't you stay aloft for 20 minutes also? I mean, it could be possible.
I think if you look at drones as they go smaller, they definitely get shorter and shorter battery life.
And I'm claiming that should not be. And if you proportioned everything the same as you would in a quadcopter, you should be able to stay aloft for 20 minutes.
I think you're right. I think there's two factors that are coming into play that make smaller drones have a shorter battery life. One of it is just more friction. The viscous friction becomes a little more as you go smaller, relatively speaking. I don't think that's the main reason. I think part of it is that there hasn't been as much effort to optimize the efficiency of them. And the other part of it is that small motors, as I alluded to, actually maybe I didn't, but motors start to get much less efficient as you go to small scale, and much less power dense. And that has to do with just simply how much, to make a powerful motor, you need to shoot lots of current through a tiny electrical coil. And as you make those coils smaller and smaller, there's less room to have a thick coil to have the low resistance you need to be efficient. And so motors scale down pretty ineffectively.
I think that's for motors, but you were using this very clever bimorph.
Right. So in theory, the piezos don't they scale down more favorably. They don't have the same losses, the magnetic heat losses that motors do. So in theory, they should do okay. The reason I think we're not there yet, and I have reason I think that we're going to find much more efficiency in the future, is that first of all, the anticipated short battery lifetime partly comes from the fact that we're still carrying a sensor payload that's about as heavy as the whole mechanical payload, whereas at larger scales, your sensor payload is a tiny little thing on this 6 kilogram drone. So maybe it's not that small, but it's a much smaller fraction of the weight of the robot. I have reason to think that's possible to get much smaller, this sensor platform, through by integrating all these components onto the same chip potentially. So that's part of it, is just the electronics gets much heavier, relatively speaking, as you go small scale. We also haven't we've been focusing on control, so we haven't done a lot of efficiency optimization on the piezo mechanism and the flapping wing mechanism. There's a lot of, we're doing the kind of ready, fire, aim approach. We get something working and we go on to the next thing, and then we go back and try to make it more efficient. So I think there's a lot of room to improve the efficiency of the piezo mechanism and the aerodynamics that we haven't really tapped into yet. I don't know what sort of efficiency, factor of 2, factor of 4, or something like that is.
Yeah, I'm sure you can improve things, but it's good to compare with other things. For example, jumbo jets. Jumbo jets can stay aloft for 19 hours.
Yeah.
And the reason is that jet fuel has much more energy density than lithium batteries.
Yeah.
But then it suggests something different. Why can't you have sort of a consumable battery? For example, there are batteries that actually run on glucose. And now, not that that's the most efficient, but you can imagine some kind of fuel cell or something where you're using fuel which has much higher energy density than lithium batteries.
Yeah, that seems totally possible. That would be great to have something like that. Yeah, something that combusts. My understanding is that combustion-powered scaling doesn't help you. It's really hard to make a small combustion engine
Right, right. Don't make a combustion engine. Look
Yeah.
at the combustion inside the insect.
Yeah.
The inside is, the insect is consuming glucose,
Yeah. Yeah.
and it's
Yeah.
actually burning the glucose.
Yeah. They have the Krebs cycle and ATP and loads of membranes and the actin-myosin system.
Yeah, but it doesn't have to be that complicated. There are batteries that actually run on glucose, and certainly there are the diabetic sensors, the glucose sensors for people with diabetes. Those are little batteries.
Huh. Okay. Okay. The other thing we need is a high current density, which doesn't hold for most batteries. Do you happen to know what the sort of current, are they able to get high current densities?
Well, I think the fly needs energy 24 hours a day. You want everything done in let's say 20 minutes. You're now at 2 minutes. You'd like to get to 20 minutes. So yes, that might be a problem.
But that's very interesting. Yeah, I'd love to know more about that. I don't know.
Just think of it as flow batteries.
What would I search for? Just glucose fuel cells, something like that?
Something like that, yeah.
Yeah, okay. And what are they used for? In glucose monitors, something like that?
They're used in glucose monitoring where you're not, you're just sensing then, you're not producing power. But the flow batteries, you just have some energy-rich liquid, and it gets oxidized. And with a catalyst, maybe it'll go faster. So you're trying to match 20 minutes of flight time.
I mean, that's interesting. So apparently the catalysts on fuel cells, they tend to be very expensive materials, but if you have a tiny fuel cell, it doesn't matter.
Sure.
Platinum. That's interesting.
Sure.
Huh.
Someone might steal your flies.
It's like a RoboFly diet. What do you feed them to?
Yeah. Well, if they could feed themselves, that'd be great. Yeah.
Yeah. I wanted to go, we had a Jay Payne who had a couple of questions. I'm gonna go ahead and let Jay ask the question directly. Jay, welcome.
Hi, good evening, everybody. Thank you. I appreciate the entire session. It was awesome. So I teach students, you're welcome. So Dr. Fuller, I teach students here in Barbados, ages 6 and up. And I was thinking of two questions. What types of payload applications would such a small robot be useful for? So you can answer that, and then I'll ask the second.
Okay. Payload applications. That's a great question. I have hope that eventually down the road, it might be possible to use this type of robot to assemble in a way inspired by what termites do, which tiny termites carry tiny clods of sand or wood and build giant things much larger than themselves. There's no reason that insect robot couldn't do the same thing. It just requires a very precise ability to localize yourself. So I've always thought of it as something that would be very amazing eventually, a swarm of these guys, millions of them building a house or something like that out of tiny little bricks. But it's always been something that's a little bit farther off because it requires in some sense, kind of mysterious abilities. Like how do you make all these robots cooperate together in a holistic way? But that's the best example I can think of some example of where a payload that you'd want one of these to carry. That's maybe the only one I can think of at the moment.
Absolutely, awesome. It was really interesting because I know you gave two examples initially at the start of the session, and I love those. Especially as industrial applications. But then I was thinking, okay, so what types of useful activities would such a size, which is limited in payload amount, would be useful for? So thank you for your answer. And the second question is, well, I don't know if you might know this, but as an educator, for me, this is useful. I'm excited to take this information back to my students. So what is the smallest robot kit that maybe you could recommend for students who are in high school? I would say maybe ages 15 to 18. I wouldn't go any younger just yet.
15 to 18. The first one I was going to suggest are these so-called toothbrush robots. They consist of a vibrating motor and a you can actually just glue them to the, I think there's demonstrations of this, or instructions for this. We glue a motor to a toothbrush, and it, through the vibration, it walks along the ground. I think there are kits you can buy from this. Where would you buy this? Let me think, where have I seen these available?
No, that's okay, because I know exactly what you mean. Yeah, that's
okay.
A good point.
Okay, but that's not autonomous, but it's still, they do really cool things. So like larger robots. So you're thinking of like having a platform that you can have a little bit of autonomy for 15 to 18-year-olds. My son is 5, so I kind of know, I know everything that happens below 5. I know it's between 5 and 15, unfortunately.
That's all right. That's all right.
Yeah, Mindstorms comes to mind, but so that's yeah. Are you aware of Mindstorms, Lego Mindstorms?
Yeah, so I'm aware of Mindstorms and Vex and so on, which are, very nice modular kits and so on.
Okay.
Sometimes you might think that you've seen everything, but you don't know if you have.
Sure.
So I was wondering, maybe there was something that you knew out there that I maybe had not researched yet. And so that's why I was asking the question, to see if maybe someone, I mean, it could be anyone, whether panelist or someone from the audience can recommend anything at all. Because I like to introduce students from a very early age to the possibilities. So then that way, it actually drives their thinking from early. So then when they get to your level, PhD status and beyond, it's, this is something that has been ingrained in them. I'm sure you probably understand the same with your son.
Here's one other one. I think it'd be awesome if somebody made a kit for like $10 or $20 or something, so that anybody could just be an impulse buy. I'm going to post in the comment one other one, but it's a little more pricey. It's $130, so it's kind of like Mindstorm's price, a little bit less. But it's another one that I recently heard of. A Root robot drives around on a whiteboard, magnetic whiteboard.
Thank you so much.
So sorry. Thank you, Jay. Great questions. I'm gonna drop some things in the chat. There was actually a $10 robotic challenge that was put out a couple years ago by Citrus here at Berkeley, and I'm gonna drop some links because there was some really great winning designs, and they're low cost. So maybe those will inspire you and your students. I would love to see that happen.
Awesome.
Great. I want to be respectful of people's time. Maybe this last question from Alex Mornero. I'm going to make you kind of promote you up here, Alex.
Hello?
Yes, we hear you.
Yeah. So I guess my first question was, how big was the camera that you were using? I don't remember seeing anything about pixel dimensions and stuff like that. So that was my first question.
Mm-hmm. The camera is about 100 by 100 pixels. There's two imagers we've used. One is a diode based from Sentai, and I think that's 100, might be 120 by 120. The other one is a commercial camera by Himax that's also super low power, and it's also about, I think, 120 by 160, something like that. That's quite an impressive little camera because it only uses 3 milliwatts, which is pretty cool.
Yeah, it's really good. So wait, so do you use both of them for different parts? Like, are you using one from like range and the other one for your optical flow?
Let's see. So the rangefinder is a VCSEL-based laser device you can off the shelf from ST Microelectronics. It measures time of flight of a laser pulse. And then we're using a downward-facing optic flow camera. That's what we're intending to use. That's either the Sentai camera or the Himax camera that measures angular velocity. Did that answer your question?
Yeah, thank you. Cool. And then the other question is, are you all doing any sort of like wireless like networking or for swarm robotics?
Yeah. Couple comments there. Yes, definitely. We're working right now on integrating a Bluetooth chip, partly so we can do off-board computation and then slowly move it on board. Bluetooth is great for this application. Eventually, I think we'll have them networked. I don't think that we're going to be doing something like cloud robotics on these platforms where you collect your data, send it up to the cloud, you do some deep learning on it or deep process inference or whatever, and then send it back to the robot, because that ends up using a fair amount of power. Bluetooth uses up to 20 milliwatts, which starts to be a pretty significant power waste or usage at a 60 milliwatt RoboFly. That said, intermittent communication, I think would be super valuable, especially, if you're looking for a plume of a gas, for example, there's people have been working on algorithms that if you have many robots working together and they communicate with each other, they can find the plume much more quickly than if it's just one at a time. So I think we're in my lab, we're really happy when we have one flying well. we have yet to fly two, but eventually we'd like to have lots flying, and then at that point we need to do communication between the robots.
Awesome. All right. And I guess
Great.
one
Thank
last.
you, Alex. Oh, sorry.
Okay,
We better move on.
Yeah, thank you.
Is it a quick question, or what, if it's quick, that's fine?
I probably can. I was going to ask about like the power breakdown, because I was like wondering how that kind of looks like for like the actuation versus the sensors versus how much more they would have left over for the wireless. So it's probably a lot more than a few minutes.
Roughly speaking, we'd allocate about 10% to the sensors and processings, and that ends up being on the order of 20 milliwatts for all the sensors that I talked about. And then flight power is on the order of 200 milliwatts. So something like that.
Thank you.
Sure.
Great. Thank you. Great questions, everyone. Thanks, Alex. Thanks, Jay. Thanks, Dylan and Daniel. Had some great questions. So I also want to make sure we definitely thank Sawyer Fuller. This was super inspiring. I'm going to look out in the air and watch for your future robots to land on the trees and plants in my backyard. But really inspiring work. And I'm glad you were able to come spend time with us here at Berkeley, even through our little bits and our little windows. I really appreciate it. Eli, do you want to add anything?
It was great, and I wish we could now take you out to dinner, but we'll find an occasion.
Sounds great. Sounds great. Thank you so much for having me. Appreciate it.
Great. And thank you all for attending. We will see you in 2 weeks. Be safe during spring break, please. This is for the Berkeley students, but all right. Thank you.